All right, let's talk about more reductions. Another style of reduction is with the Grignards. I like to call it adding magical carbons to a situation. You start off with a carbonyl, you're given a carbon chain, which is derived from an alkyl halide, and then you're going to get an alcohol, but also with those magical carbons. So what you start with is going to look something like a carbonyl compound given with a magnesium halide, alkyl magnesium halide, with THF, which is just an ether solvent, and acid. Now, in order to make making an alkyl halide, it's not really making an alkyl halide, it's making a magnesium halide. What we have to do with that is we start off with an alkyl halide and then we insert magnesium into the situation. Now, how does that change up the reaction? Let's go back to a little bit of Orgo 1, understanding that Br is more electronegative than carbon, which would be that the Br is stronger, denoted by the dipole negative sign, and this one with the positive. So when we end up adding magnesium to the situation, it's going to change the polarity of the carbon. So all of this, instead of being electronegative, this whole thing becomes electropositive, and the carbon actually becomes electronegative. That means I can now, making the carbon a nucleophile allows it to be added to the actual carbonyl structure. So let's go ahead and count. Anytime we're doing our addition, we want to make sure that we're counting from the magnesium side, the first carbon over. So this would be carbon 1, 2, 3, 4. So I'm using that magnesium halide to add to the carbonyl. This is the full length mechanism, so I'm just going to use the exact structure of what we have there. And understand it's now going to be this carbon, which is electronegative, that needs to attack somewhere over here. So with all mechanisms, you should know now that all mechanisms go from nucleophile to electrophile. So over here, we need to find what's delta positive. So if the oxygen is negative, that lets me know the carbon is electropositive. This is a real good way to remind yourself how to do your arrow movements. So this carbon is going to attack this carbon and then open up the carbonyl, the double bond, so it's going to break that. When it does, the MgBr is also going to do its own dissociation. So this part now looks, if the oxygen breaks open, remembering our formal charges, oxygen should have 2 bonds to be stable. When it has 1, it will get a negative charge. The MgBr, when it pops off, remember it was delta positive. So it's gonna come over here near the oxygen to act as a balancing act. And then we had the 4 carbons starting from the magnesium that get added to the actual carbon here. So once we add, that's 1, 2, 3, 4. Make sure you're adding the right number of carbons. And then this has a negative sign. And in mechanisms, how we know we're not done is we shouldn't have any more positive and negative signs on the actual product that we want. So the next step would be the H+. Remembering H+ could be any type of water or even H3O+. It just depends on what is given to you. So I'll use H3O+ in this case, which would allow now for that negative charge to grab onto this hydrogen and kick off the water, making your final answer, scoot that up a little bit, making your final answer the oxygen turning into an OH, the magical carbons that were added being 1, 2, 3, 4, This will give you your final answer, and what breaks off here was water, and you still have the MgBr with the positive charge. That's just left over. These can still react to create something else, but byproducts are not your main concern. It's making sure that you created the structure properly. So here, this structure was called a formaldehyde, if I didn't mention it before. That formaldehyde plus magnesium bromide yields you an alcohol. Now, if you want it to be more in depth, you can say what type of alcohol. It's connected to 2 hydrogens, so that's primary. So now to do a few other pictures of other structures and problems. So again, this is the full length mechanism that you may need to know for an exam or a quiz, but now let's actually do the quick way of how we can get these answers. So now, here are some examples, and we're gonna do these the quick way without having to provide a mechanism. And that's what everyone really needs. We need time-saving techniques, because when we have those, anything is possible. So here we look at the magnesium halide that's being given, and then what we're going to do is count our number of carbons starting from the magnesium halide, and then we want to see how many. So we got the right number of carbons, right? Now what's next? Looking at your actual carbonyl to determine where to add it. You can always leave your backbone the exact same. The oxygen, the carbonyl structure will split. One will be an oxygen, the other one will start off. So that double bond will split like this, making that turn into an OH, and that first carbon here is number 1, and that's the same number 1 that's over here. And then we just add numbers 2 and 3, and that's our final answer. How cool is that? So for all of them, let's quickly go through and write the backbone of everything we've seen. Esters are special, so you have to remember, we always break them here. And we're gonna still break the oxygen in this bond, but now we're having the positive. So right now that's just me splitting the 2 pieces apart. The carbonyl is still becoming that picture. And then the carboxylic acid is also a trick. Does it really become an alcohol? We'll see shortly. So when it comes to now this structure, turn it to an alcohol. That's our first carbon. Write the number of carbons. A lot of people make a lot of mistakes with this one, and they end up either having additional carbons or losing a carbon. So really practice this technique and even the mechanism to solidify it. So again, if we had our ketone, OH, that's carbon number 1, 2, 3. The ester breaks up apart. The alcohol, or the ether portion right here, will always, this side will always become an alcohol. No matter what type of problem we're doing, it will always, absolutely always break up into the alcohol. Over here is where we need to look at it. Now, when we deal with the Grignards, I put a star there to make a notation for you that when we're doing Grignards, whether they state it or not, you're adding 2 moles. So they'll either say 2 equivalents, 2 moles, or they may even write this structure here and use the word excess to give you the hint that you need, which means you're adding it twice. So you turn the oxygen into an alcohol, then you add your piece, but then you must add another piece to the same carbon. So when drawing the line, you draw the line to the first dot, that would be number 1, and then the remaining carbons, 2, 3. It looks crazy, but it's absolutely right. So starting from a formaldehyde, we get a primary alcohol, An aldehyde yields us a secondary alcohol. Ketones yield tertiary. Esters yield tertiary. And again, this will always become an alcohol. It just depends on the group that's attached. In this case, it was primary. Now with a carboxylic acid, let's have a quick conversation. If I have this MBr, Mg, and I know this carbon is negative, this negatively charged carbon, will it really want to go to the carbon that's electropositive or the hydrogen? So in this case, we have two things that are areas that are attracting the nucleophilic charge. The nucleophilic charge would love to attack at the carbonyl. However, in this case, because hydrogen is smaller, it's gonna wanna gravitate towards grabbing this hydrogen instead, and then leaving the rest of this untouched. So what I mean by that is this negative charge picks up this hydrogen, and then the bond, the rest of the lone pairs fall on the original structure. So we do not get a alcohol for this picture because this becomes an O-. The MgBr holds as a placeholder to stabilize this. This is called a carboxylate anion. And then the structure here, again, your carbon chain, which is 1, 2, 3, ends up going to pick up that hydrogen. So on number 1, we just needed a hydrogen attached. So that gives you an alkane. Now, for your instructor, the instructor may want you to actually show the carboxylate anion and the alkane, or they may just allow you to say no reaction. I would advise you to look back at your notes, because if they state no reaction, it's still a true statement, because does carboxylic acid with a Grignards yield an alcohol? The answer is no. So that's why we would state it as no reaction. But double check on your notes and make sure you really understand the mechanism and the quick way to apply this problem, because we need time-saving techniques to really help us get through practice problems.